In these chapters, we will discuss the theory of GLMs and how to apply these methods to applications. But first of all, we have to know how the step constructions of GLM. There are four outlines. First, introductions to IWLS algorithm for interconnected GLMs. Third, IWLS algorithm to augmented GLMs. And lastly, IWLS algorithm for XGLM. To begin with, LGLMs extended GLMs by allowing random effects in the linear predictors. Also, XGLMs allow regression models for the residual variance and the variance for random effects. In line with this, Lee, Nader and Pawitans in 2017 and Ha, Young and Lee 2017 described both the X-likelihood method and IWLS algorithm with related theories. In these chapters, we show how XGLMs can be fit using interconnected and augmented GLM. To join linear model for mean and dispersions, we can consider a linear models just like these models y equals to x beta plus e, with the e follow normal distributions with mean 0 and variance c. And our c is the diagonal from the ci. The maximum likelihood estimator for b is beta hat, which is the x transpose c inverse x inverse with the x transpose c inverse y. Now, suppose that we have a regression model for the dispersion Ci. So our G Ci should be big G, I, and our gamma, where G dot is a link functions and big Gi is the ith row in the descent matrix G. The maximum likelihood estimates of the regression coefficients of the dispersions gamma can be computed by using E hat square as response in the gamma GLM with mean Ci. The RML estimates can also be computed by using EI hat square divided by 1 minus Ki as response in the gamma GLM, which having a prior weight, we can do the calculatings 1 minus Ki divided by 2, where the Ki is the ith diagonal element in the hat matrix. With that, we have this hat matrix, which is H equals to X transpose C inverse X transpose C inverse. Suppose Y follows the GLM class of model with the eta equals to X beta, with the expectations value Yi equals to mu I, with the calculating by variance Yi with the Ci V mu I. And dispersion Ci follows the regression model with the G Ci, with the big G gamma, where the G dot is a link functions and big G is the ith row in the descent matrix. Given Ci, the maximum likelihood estimators beta hat can be obtained by using IWLS algorithm for GLM model, with the prior weight 1 divided by Ci. With full algorithm, you can see in the chapter 2. As follows this equation. Given beta, the ML estimate for the regression coefficients of the dispersion model gamma can be computed by using the deviance D as response in gamma GM with the mean Ci. Therefore, the ML estimates can be computed by using Di divided by 1 minus Ki as response in a gamma GLM having a prior weight 1 minus Ki divided by 2, where the Ki is the ith diagonal element in the hat matrix. Following this. So, this figures illustrates that join GLMs for mean and dispersion. And we can consider the linear mixed model Y equals to X beta plus ZV plus E. The model can be written as an augmented linear model as YA XA delta plus EA. Therefore, the model can be rewritten as an augmented linear model, which is we have YA equals to XA delta plus IA. And the conditions like this. The variance covariance matrix of the augmented residual vectors is given by variance from the EA, which is from the W inverse. And the data augmented method can be used to fit random effects V. Linear mixed model. The estimates from the weighted least squares are given by these equations. X transpose S W XA delta hat equals to X transpose A W Y A, which is identical to Henderson's mixed model equations. In line with this, we can extend the estimation method for joining GLMs to JLMs by including random effect by augmenting the response vector. The weight matrix W may then be updated using the estimate variance components, and the algorithms iterates until convergence. Following by Lee and Nelders in 2001 showed that the augmented linear models can be extended to fit the SGLM class models. XGLM class of models. XGLM has two random components. First, a response Y and observed random effect V, such that Y with conditions V follows a GLM distributions, namely normal, binomial, Poisson, or gamma. Therefore, the expectations of the conditional model with Y with conditions V is written like this. We have expectations value for Y with condition U equals to mu, and our G mu equals to X beta plus Z V, and we can get the V, which is the R U, where the G dot is a link functions, X and Z are design matrices, and B is our fixed effect. The distributions of U is one of the conjugate distributions of GLM family, including binormal, beta, gamma, or inverse gamma. Therefore, the random effect V is given on an appropriate by with canonical scale through the link functions R dot transforming U to guarantee correct model estimator. IWLS algorithm for SGLMs. To begin with, we can consider the heteroscedastic linear mixed model following these questions. With the independent and heteroscedastic random effect, Vi follows and with the mean 0 and variance lambda I, and the residuals IE follows the normal with the mean 0 and variance Ci. Now, we can allow GLMs for dispersions or residual variance and random effect variance following G1 Ci and G2 lambda I. By taking log link for these variance components, we avoid negative estimates for variance components. The data augmentation method is used to fit the model. The IEML estimates for gamma 1 can be obtained by applying a gamma GLM to the response EI hat square divided by Y minus Ki, with the weight Y minus Ki divided by 2 for I, 1, 2 until end. Those for gamma 2 are computed by applying a gamma GLM for the response Vi hat square divided by 1 minus Ki for I, which is n plus 1, n plus 2 until n plus m. And the hat value Ki are obtained for the hat matrix of the augmented model. Therefore, these figures represents interconnect GLMs for XGLM with structure dispersion. Now, we can consider a SGLM such that 2 points. Point 1, Y with conditions V follows a GLM distributions with the eta equals to X beta plus ZV. And second, U follows any conjugate distributions of GLM family with the G1 Ci equals to big G1 I gamma 1 and G2 lambda I equals to big G2 I gamma 2. Then, the IEM estimates for gamma 1 can be obtained by applying a gamma GLM to the response di divided by 1 minus ki, with the weight 1 minus ki divided by 2, where d here is the deviance for y with conditions phi, GLM for I equals to 1 until end. Those four gammas are computed by applying gamma GLM to the response di divided by y minus ki, where d here is the deviance for v GLM for I n plus 1 until n plus m. In addition, we allow various GLMs to y and c in the augmented response to fit random effect model. Lastly, we use interconnected joint GLM fit for mean and distribution c and lambda. To give an example, open the Advertus Analytics and select the Epilepsy. We have 7 variables: Y, T, B, AV, patients, and ID. And we can write our Poisson GLMs as follows. We have log mu Ag equals to beta 0 plus beta Bi xb plus beta T xt plus beta AI xa plus beta V g xv plus beta Bg Ti x bt. First of all, the over dispersion Poisson GLM. Poisson GLM gives a deviance of 899.9 with degrees of freedom 230. Clearly indicate over dispersions. Click the regressions, click join GLM, check use for model for V, select independent variable T, B, A, V, and BT. Therefore, this is our models. We get the all of significance level from our variables is less than 5%. Therefore, our variable is significant. And to measure the error, see the likelihood table with the minus 2 ml, minus 2 rl, CISC, scale deviance, and degree of freedom. Therefore, change the additional settings, method of estimating fee by percent. And we can get our fee. $1.50531 for our estimate intercept. This is the result. Because the deviance residual are the best normalizing transformations under the exponential family, it gives an estimators with small variance, but it gives us inconsistent estimates. Following by Hilby in 2014, recommended to use the percent chi-square statistics because it gives a consistent estimators. In infinity sample, the deviance often gives more efficient estimators, following by Nether and Lee 1992. Thus, it is recommended to use the deviance in small samples. Correlations among repeated measures should be considered, so XGLM should be used for further analysis. Open the Albatros, browse the data injections, and this is our data. Injections, which is the in-industrial Taguchi experiment, was performed to study in the influence of several controllable factors on the mean value and the variations in the percentage of shrinkage of products made by injection molding, following by Angels 1992. Which is we have Y, percentage of shrinking of product made by injection molding, and we have 3 noise factors and 7 controllable factors. This dataset has been attended by many researchers because the model checking plots were not satisfactory. Following by Lee and others in 1997 gave extensive discussions on how to choose a good models and present the heteroscedastic log linear models, model with log normal distributions, and the identity link eta equals by mu. And the mean model eta equals to beta 0 plus beta A big A plus beta CC plus beta DD plus beta EE plus beta GG plus beta NN plus beta C and CN plus beta E and E and. Open the Albertus Analytics, click Regressions, click Join GLM, select independent variable A, C, D, I, G, N, C, and I, N. Click long functions, select identity. For model V, select independent variables A and F. Click run. And this is our estimates parameter for V. To measure all models, click model checking plot. This is the scatter plot of residuals versus fitted. The next study case is crab growth. The crack growth data from the experiments where the crack length in the inches are measured on the component tension steel test or studi test, operate in different laboratories, following by Hudak et al. In 1978. Therefore, we have one independent variable, y, increment of crack length, and three independent variables, crack zero, cycle, and specimen. And we can return our gamma GLMs like this. You have eta equals to log mu equals to alpha plus beta crack 0. Gamma GLM with structured distributions, we may estimate our C either based on definitions or percent chi-square statistics. In the example, the degrees of freedom is large, which is 239. We may prefer the percent chi-square statistic in estimating C. Open the Albertus Analytics, Regressions, Log linear model, select independent variable click 0, select the distributions gamma, and for the model for V, select independent variable cycle. And this is our model. We get the estimate of cycle minus 10.30. Click model checking plot. This is the scatter plot of our residual versus fitted. The next example, this dataset is bacteria datasets. Test of the presence of the bacteria X influenza in the children with the otitis media in the Northern Territory of Australia. We have Y, 1 for presence and 0 for absence, AP, A for active and P for placebo, high-low, high for high compliance and low for low compliance. We have week, the number of week at test 0, 2, 4, 6, 11. ID, subject ID, TRT, the placebo, drug, A and low, drug plus A and XI. We can return our binomial GLMM with the PIG followed by PYIG equals to 1 with conditions VI. Hence, this VI follow the normal distributions with mean 0 and the variance lambda. And we can write our models like this. Albertus, select random effect model, choose generalized linear mixed model, select the response Y, and independent TRT, random effect ID, distributions binomial, For additional setting, you can choose REML or ML. But for these cases, we choose REML. Click 1. This is our model summary. The slide previous step, if you want to see the model measurement, click the model checking plot to see our residual.